Hi, I'm Dane Quinn from the University of Akron, and today's video lecture will be concerned with vectors. So, really, the question is, why do we care about vectors? Well, it's because the elements of dynamics, which include position, acceleration, and things like forces and moments, are naturally described by vector quantities. So if I ask, what is a vector? Well, it's this mathematical quantity that describes multiple independent variables. And in particular, it's used to describe physical objects that have both magnitude and direction. Now, vectors obey the laws of things like vector addition and scalar multiplication, which we'll talk about in a bit. And then there are additional operations, such as the dot product or the cross product, that vectors follow. Right, so let's look at a vector. And so we'll draw one. Right? It's going to be some vector here. And we'll describe this, and we'll label it as R. Right? So R is a vector. Right? So the vector R can be defined in a number of different ways. Right? So in particular, it can be defined geometrically in space. And so we often think about vectors as arrows, right? So we have this arrow here that kind of starts here and goes there, right? And that arrow represents a vector. And in particular, this vector is independent of how we choose to measure. So it's independent of the measurements that we choose to describe it. And so kind of this vector is the vector. If I say, look, we have this vector R, it's described by this arrow, that's enough. We don't really need to define anything else about the vector. Now we can certainly measure lots of different things about this vector, but it's defined sort of independent of our choice of measurements. Now just a little bit of notation. Vectors are denoted in these notes with underbars. So if you look at the label here, we have a little bar that is underneath the letter R. So R is the name of the vector, and we always add a little underbar to denote that R is a vector. Now, if there's no underbar here, that would imply that R is a scalar quantity with no direction. So it would just be a single independent quantity. But again, vectors have multiple independent variables, and we use underbars to denote those. The only exception is in the case of unit vectors. So those are going to be useful for indicating bases or specific directions. So unit vectors, by definition, have length 1. And those get denoted with an overhat. So this is just a little notation that we will use fairly consistently in these notes. Right? So this might be I hat. Right? So this underbar denotes a general vector, sort of arbitrary length, and the little hat denotes a unit vector. Right? So that's a special vector that can vary in direction, but always has fixed length. And that's going to help us keep straight the various quantities that we'll use, including sort of vectors like position and velocity and acceleration, from vectors like I and J, which indicate direction. So now, speaking of directions, vectors are specified with respect to known directions. So again, here I have some vector. We'll call it R once again. So we need a set of directions that we define as basis directions in order to measure the vector R. So we have a number of different choices. We could choose, for example, I and j. Right? So these are going to be Cartesian directions that are fixed in the ground, or the frame of reference. In this case, it's sort of the computer screen or the paper that we're working on here. So these directions never change. So I could say, I is horizontal, for example, and j is vertical, like so. Now, these aren't the only directions that we could define. I could also define directions that move with the object. So those might be polar directions, and we'll define E1 and E2 as a set of polar directions. And those, again, move with the vector. So we might say that the direction of r is in the E1 direction. And again, as r moves around, E1 moves around with it. And then I could have a second direction, E2, which is orthogonal or perpendicular to E1. So we might have E1 and E2 that move with the vector, and these two things might be related by some angle. Right? We can call that angle, say, theta. So now, in terms of these different directions, we can describe r as, well, let's use I and j first. Right? So assume that the horizontal component is x and the vertical component is y. So here, r would be x in the I direction and y in the j direction. So as r changes, x and y could vary, but the directions I and j remain fixed. Alternatively, we could describe the length of this vector as r. And again, look at the notation. This r doesn't have an underbar. It's a scalar, so it represents the length of this vector. This r is a different quantity. It's the vector r. So in terms of the polar directions E1, E2, we would have r in the E1 direction. Right? So now, if the vector r changed, the length might change and the direction might change with respect to the ground. But here we have the same vector expressed in two different sets of directions. Remember what we said in the last slide, that vectors are defined independent of how we choose to measure them. Now, of course, if we have I and j and E1 and E2, might be a useful thing to relate those two sets of directions. And we can certainly do this. Right? So here I have I and j and E1 and E2 written out, and we'll let theta be the angle between them. So, for example, I could express E1 and E2 in terms of I and j. Right? So if I choose to do that, I think the best way of looking at this is with some triangle where the perpendicular sides are in the I and j direction, and then the hypotenuse is, for example, E1. So if I look at this triangle, then we see that this side is cosine of theta. Right? So here, a little more shorthand. Cosine of theta I will often abbreviate like so. And, of course, sine of theta I will abbreviate as s theta. But this side has length cosine theta, just a little trigonometry. And, of course, this side has length sine of theta. So if I want to move from, for example, this point to this point at the end of this vector, right? So if I want to look at this vector, I would have to go a distance of cosine of theta in the I direction and sine of theta in the j direction. Right? So I kind of walk this way and then walk in the j direction to get to the end of E1. Now I can do the same thing for E2. Right? So we would draw that angle, or that triangle, and that interior angle is theta. So we see that E2 now is, well, notice that in order to go from here to here, I have to walk in the minus I direction. Right? So we'll say minus sine of theta in the I direction and cosine of theta in the j direction. This description is valid for any angle theta. Right? So even if you take an angle of like 225 degrees, which would put E1 in the third quadrant, everything still works out because sines and cosines would have the right sign, sign, plus or minus 1. And this would be a valid description. So here I've related E1 and E2 in terms of I and j, but I can go the other way. Right? Again, this interior angle is theta, as is this one. So if I wanted to write I in terms of E1 and E2, again, I would walk some distance in the E1 direction, and then I would walk some distance in the E2 direction. This length would be cosine of theta, and this length would be sine of theta. So immediately we would see that I is, well, how far in the E1 direction? It is cosine of theta in the E1 direction. How far in the E2? Well, now, again, if theta's positive and some small angle, we would walk in the minus E2 direction. So we have minus sine theta E2. Likewise, for j, we would be dealing with sort of this triangle. So in the E1 direction, we would have j is equal to sine of theta E1, and then plus cosine of theta E2. So given these directions and the angle between them, I can relate E1 and E2 to I and j, or I can relate I and j to E1 and E2, and I can go back and forth between the two. So now, in terms of this, we can actually use this, for example, to relate x and y and r, and in fact the angle theta as well. So notice that r is equal to x in the I direction plus y in the j direction, and that's also equal to r in the E1 direction. But here, E1, we have already found, is cosine of theta in the I direction plus sine of theta in the j direction. So, collecting all this stuff, in the I direction we have r cosine of theta and r sine of theta in the j direction. So now looking at the left and the right hand sides, the component of I on the left has to equal the component of I on the right. So x is equal to r cosine of theta, and similarly for j, y is equal to r sine of theta. So we can oftentimes come up with coordinate transformations based on the geometry of these different bases directions. So now, we had said that vectors obey a number of different laws, including vector addition, right, which we'll look at first, and scalar multiplication. So here, assume that I have three vectors. Right? I have some vector, say, c, and c is going to be equal to a plus b. So a will be this vector, and b will be this vector. So again, just geometrically, the vector c is the vector a to here plus the vector b to there. Well, these are defined, of course, independent of any directions or coordinates, but let's use, say, coordinates or directions I and j in order to describe these vectors. So now, taking components of these vectors in the I and the j direction, then the vector c is described here. So we'll say this is xc and yc. So again, the vector c is xc in the I direction, yc in the j direction. Now let's look at a we would have x a and y a, and then for the vector b, xb and yb. Now notice that here this component of b in the j direction is downward, so yb would be a negative number in this case. So we would have, for example, something 4 maybe in the I direction, minus 2 in the j direction. So again, yb in this case would be negative. But the vector a is xa in the I direction. Again, ya in the j direction. The vector b is xb in the I direction and yb in the j direction. So now looking at this law of vector addition, xc plus yc in the j direction is xa in the I direction, ya in the j direction, plus xb in the I direction, yb in the j direction. As a result, right, we can again compare the left and the right hand sides and show that xc is xa plus xb, while y, the component of c in the j direction, is ya plus yb. And that makes total sense. So here, this value xc is the component of a in the I direction plus the component of b in the I direction, while yc is the component of a in the j direction and the component of b in the j direction. Once again, in this case, as shown, as drawn in this figure, yb would be negative. So we're able to relate the components based on this sort of vector addition law. Now we also have a law for scalar multiplication, right? So let's let d be this blue vector here. And once again, d is going to be some component in the I direction and a component in the j direction. And so, for example, if I take 2 times d, we actually find this green vector, something with the same direction but twice the length, right? So this was the original vector, this is twice the vector. So 2 times d is 2 xd in the I direction and 2 times yd in the j direction. Likewise, if I had a vector minus d, then that would be in the opposite direction of d, but in this case the same magnitude. Right, so the components would be minus xd in the I direction, minus yd in the j direction. So for scalar multiplication, it leaves the vector direction unchanged. And only changes the magnitude of the vector. But again, the direction of the vector remains the same as before. So we have two other operations that we mentioned initially. One was the dot product. So the vector dot product, it operates on two vectors. So it's kind of like multiplication, right? But it's not the same. It operates on two vectors, and it produces a scalar, just a single number. So now, If we have perpendicular vectors, then their dot product is 0. So, for example, if I have my directions I and j as before, we find that I dot I is equal to 1. So the dot product of any vector with itself is simply the length squared. And at this point, you've probably been introduced to dot products and even cross products, right? So this should be some review. I dot I is equal to 1. J dot j is also equal to 1. But I dot j, because they're perpendicular, is equal to 0. So notice that each of these objects on the left is a vector, and on the right we have simply a scalar quantity. So now let's go and look at two arbitrary vectors, say A and B. So here, let A be equal to xa in the I direction plus ya in the j direction, and let B be equal to xb in the I direction and yb in the j direction. So A dot B is xa I ya j dot xb I plus yb in the j direction. So if I expand this out, we have xa times xb times here I dot I. Now we have ya xb j dot I. We have xa yb I dot j ya yb j dot j. So now, looking at this, we also, from here, find that j dot I is equal to 0 because those are perpendicular. And we find that I dot I, again, is 1. J dot j is equal to 1. But j dot I is 0, and I dot j is 0. So ultimately, A dot B is xa xb plus ya yb. And notice that this is actually equal to B dot A. So the order here in terms of the dot product doesn't matter. A dot B is equal to B dot A. So now one special case occurs when one of these vectors is a unit vector. Right, so let's say that E is this vector here, and A represents some arbitrary vector. So here, if I look at the dot product between A and E, we find that this is the projection of A in the E direction. So if I looked at the projection of A down onto this E direction, then this length is A dot E. So the other important thing is that the magnitude, and we had said this earlier, of the vector, which we will represent with the following notation. Notice that here we have 2 bars on either side rather than 1. It's not quite an absolute value. It's the magnitude, which is something slightly different. But this can be defined as the square root of A dot A. We had said earlier that if I take a vector and dot it with itself, I get the length squared. So the magnitude, or the length, is the square root of that quantity. And working through something like we did up here, we can see that the magnitude is the square root of x squared, xa squared, plus ya squared. Again, these are the components in the I and j direction. And you can also get this from simple geometry and just sort of looking at the appropriate triangle. So the final operation that we'll deal with is the cross product. So again, this is not multiplication. It's different. Multiplication is defined in terms of scalars. This is the vector cross product. So this operates on 2 vectors. So we have one vector cross another. And it produces a third vector. So again, we take 2 vectors, we cross them by each other, and we get out of that a third vector, or another vector. And the vector that results is perpendicular to the original 2. So here, if I take basis directions I, j, and k, then the vector cross product is defined in terms of what the cross product does to combinations of these 2 vectors. So for example, I cross I is equal to 0. Anytime I cross a vector with itself, I get 0. I cross j is defined as k. I cross k is minus j. Likewise, j cross I is defined as minus k. J cross j is equal to 0, and j cross k is I. And this is often taught in terms of the right-hand rule, right? So if you took your hand and put your palm in the I direction and curled your thumb to j, then the result would be in the k direction. Finishing this up, k cross I is equal to j. K cross j is equal to minus I. And k cross k, because those are in the same direction, same vector in fact, is equal to 0. So a little sort of handy way of remembering this is the following. If I take I and j and k, and then for good measure, let's write them out, continue on, start over, I and j. So if I write this out, then if I cross going this way, it's positive, right? So notice that I cross j is equal to k. That's what we had here. J cross k is equal to I. K cross I is equal to j. However, if I cross going that way, I get a negative answer. J cross I is equal to minus k. So we had here. I cross k is minus j here, and k cross j is minus I. Right, so this is just a handy way of remembering cross products. So now if I look at components again, right, so here in the light gray we have maybe I and j and k. And then let's take a vector A and cross that with a vector B. Then the result is a third vector that again is perpendicular to these two. So if I and j are defined like this, and A and B are defined in the plane of I and j, then the cross product of these two is going to be perpendicular in the k direction. So this black vector might be A cross B. So once again, we'll let the vectors be described in terms of Cartesian coordinates. So A is xa in the I plus ya in the j. B is xb in the I, yb in the j direction. So here, A cross B is, well, we can always just go and work this out. xa plus ya in the j direction cross xb in the I direction and yb in the j direction. And I'll remind you again that the cross product is not multiplication. It's something different. It's a different operation. Multiplication is defined in terms of scalars. But this is a vector cross product. So when I expand this out, I have xa xb times I cross I. I would have xa yb I cross j, ya xb j cross I, and then finally ya yb j cross j. So once again, comparing back with the cross product defined for the directions I, j, and k, we see that I cross I is equal to 0, j cross j is equal to 0. But I cross j is equal to k, while j cross I is minus k. So the result here is xa times yb, and now minus ya xb, all in the k direction. And if you were to go back and work this out, what you would find is that this quantity is actually the negative of b cross a. So with the cross product, I can't simply interchange the two original vectors. A cross b is not the same as b cross a. Instead, a cross b is the negative of b cross a. So unlike the dot product, I can't simply switch the order. Right? The order of the two vectors is, in fact, very important to determining the proper cross product. So this is just kind of a short introduction to vectors. We've talked a little bit about what they are and have given and described some of the standard operations, including vector addition, scalar multiplication, the dot product, and the cross product. And this information we will use throughout our course in dynamics because, as we said originally, the elements of dynamics, position, velocity, acceleration, forces, moments, all that kind of good stuff, and the equations of motion, right? So Newton's laws, in particular sum of the forces is mass times acceleration. Those things are defined in terms of vectors. So that's it for now. Thanks a lot, and I will see you again.